Welcome back again. This is going to be part number 7 of collective communication in MPI. We're going to continue from where we left off last time. So as you can see, I also opened up Final Cut Pro to render the first part, or the part number 6. But in the previous part, we basically have seen this example about MPI OP create, operation create, to have our own user-defined operations for reduction operations. Okay, and here I also put a note here that see MPI OP create inter before you proceed to all reduce. So let's just jump back here. So let's take a look at MPI OP create inter. So again, same story goes here. Our data type is going to be a complex number. A user-defined function is going to be defined based on sort of the prototype that the standard tells us to have an in-vec, in-out-vec, have a length, and also have a data type. So this is how it looks. So far, everything is similar as before. But then we have all these sections you have seen before. I'm not going to comment again on these stuff because we haven't talked about communicate. That's going to be the subject of chapter 7. So up to this point, what you need to basically understand is that we try to have group A and group B and try to basically communicate, to have an intercommunicator between group A and group B. And then again, the same story goes here to create that complex type and then create your own user-defined operation. And we said that when you're creating these two, you're responsible to free these resources as well. So when you commit your type, then you need to free that. So there needs to be a free sort of MPI type free associated to this complex type. And there needs to be also a free operation associated to this complex product that you can see it also in the end. This is it. And then in addition to those two, we need to also free these local communicator and intercommunicator that we have defined. We don't care about those because we haven't talked about them. And then the same story goes here. We have an array of 10 elements. But this time it is the difference is that only the root proc in group A basically is going to get the results. And that is why it basically defines this. And again, similar, so this is a story you've seen in all the blocking collective communications, the intercommunicator scenario, that the root in group A needs to send MPI root as the root. All the processes in group B, they need to send the rank of root process in group A, which is 0, and all processes in group A, which they are not the root process, they need to pass in MPI proc_null. So this is what happens. Again, I'm not going to comment on this commute yet, this MPI OP commutative, because we haven't talked about it. This is a way to basically check whether your operation is actually a commutative or not. So this is not that, let's say, important. Then we perform our reduction operation. Again, array result 10 because we have an array of 10 elements, 10 complex numbers. And then we have the complex type, which is sort of a derived data type that we have written. And we have also a complex product. That's a operation that we have defined. So this is also a user-defined operation. And then the root is going to be filled up for everybody according to what we have here. And then the communicator is not going to be MPI comworld. That's the major difference. It's going to be intercommunicator. And then after this reduction is done, in group A, process number 0, so the root process is going to get all the results and it's going to print that thing. So let's go with MPI CC MPI OP create inter and MPI run. In 4 processes, it's going to be like this. It also says that the operation is commutative. But why did we end up with a different result? Because we have 4 processes here, 4 processes here. Here we had -96 0i, and here we have 0 24i. The reason for that is we have group A and B. Which processes are in group B? Process number 2 and process number 3. So that is why we have only 2 multiplication in this case. So again, if you refer back to sort of blocking versions of collective communications, in intercommunicator scenario, usually this is the case that we define one root process at group A, and then all the processes in group B, they do that operation, whatever operation it's going to be. In this case, it was a reduction operation. And then they pass in the result into the root, which is in group A. So this is also sort of, um, um, let's say, consistent. That's the word I was looking for. This is consistent with all the other blocking collective communications in cases of intercommunicator. So let's, before that, I also forgot to show you this. I showed you MPI reduce, but I forgot to show you this MPI reduce inter. Of course, you can also have MPI reduce in scenarios when you have intercommunicator. Again, all these stuff are going to be the same. We're not going to comment on them. You have seen them over and over. And then again, we have a send buffer of 2. Receive buffer is going to be this time pointer. We are going to uniquely sort of populate every process with a rank that they have. And then only root process at group A is going to basically allocate proper space for the, let's say, result of the reduction operation. And then these are the things, again, root process is going to send MPI root as the root, this root argument here. All the processes in group B, they're going to send the rank of root process in group A, that's 0. And all the processes in group A, which are not the root process, they are going to send this MPI proc null. And then you call MPI reduce with those proper arguments. And the major difference is that you're not using the intra communicator, the MPI com world, but you're using the intercom. And then finally, the root process at group A basically prints the result. So MPI CC, MPI reduce inter, and then MPI run. You see that it gives 5, while in the case of, MPI CC, MPI reduce, if I run this, I get 6 and I get 5 here. Why? The reason for that is, what are the members of group B? The group B has members in 4 processors, of course. 0, 1, 2, 3. Group A is 0 and 1. Group B is 2 and 3. So 2 and 3 summation, if you remember, the reduction that we did was MPI sum for the operation. So summation of 2 and 3 is 5. So that is why root is always basically saying that I'm getting 5 and 5. In this case, it's different because it's done in intra-communicator and it's the summation of 0, 1, 2, and 3. That is why we end up with this value of 6. Okay, now we have an all reduce, which in this case, the result of the reduction operation is going to get returned into all processes. So we're not going to spend too much time because this is exactly similar to reduce operation. We're going to have send buffer, receive buffer, count, data type, operation, come. But note that this receive buffer, it's not only significant at the root, but also significant at the other processes. So we can take a look at MPI. What's the example? It's MPI all reduce. All reduce.c. So again, we have a send buffer of 2 elements, receive buffer of 2 elements. We uniquely populate it, and then we call MPI all reduce with proper arguments. And then in this case, we have rank 0 and rank 1 showing their results. But if it's 4 processes, you can also continue putting an else if here for rank 2, for rank 3. But we didn't want to have like a messy output. We are only printing rank 0 and rank 1 outputs, which they should be the same, right? Because it's going to be, the result of the reduction operation is going to be the same for every sort of process. So I'm going to compile this and then try to run it. And then you see that the root process, process 0, is going to return the sum as being 6, and proc number 1 also is returning the same result. No wonder, right? So this is the syntax and semantics of basically, by the way, we haven't talked about this one, but you can also use the in-place option for intercommunicators specified by passing the MPI in-place argument to send buffer at all processes. You can also, of course, do that, but we haven't done it in this time. So this example is not important. We have our own examples. We have another sort of variation or another flavor of this. The functions in this section are of importance to library implementers who may want to implement special reduction patterns that are otherwise not easily covered by the standard MPI operations. The following function applies a reduction operator to local arguments. So this is something called as MPI reduce local. We can also take a look at this. We have an in buffer, in out buffer, count, data type, and operation. You can see there is no sign of root process because it's going to be local. It's going to be done. This reduction operation is going to be done locally on each process. So that is what is happening. And I also mentioned no root, no com arguments because there's also no communicator argument here because, as I said, it's a local reduction operation. Note that here one important thing is that the MPI in place option is not allowed in this case. This is super important. And reduction operations can be queried for their commutativity. This is we have seen that with MPI OP commute. Oh, this is the context that I was talking about, that this comes later in the text. And this is MPI OP commutative, which we have seen in MPI OP create. In this example, for example, we saw it. Commutative. MPI OP commutative. It takes what arguments? It takes an operation, which is the complex product here. It takes a commute, that's the output. And it's also in C bindings, you see that it's an int star, so it's an integer. So that is why we pass in commute here. We let's say create an integer called commute, and then we pass the address of that. And as a result of this sort of function, we check in rank 0 whether if the commute is 1, then it means that the operation is commutative. And if it's not 1, it's going to be not commutative. So this is simply what we have seen, but we haven't talked about it. So reduce local, where's the example? MPI reduce local, vim MPI reduce local. Same drill here. We're going to have buffer this time with 5 elements and 5 elements and 2 buffers. First buffer, second buffer, and then we're going to populate it with the rank. The second buffer, we're going to populate it with the rank. Maybe the second loop wasn't necessary because I could have used the first one to populate both of them with the rank. But anyways, and then you do this MPI reduce local. You pass in the buffer, the first buffer, you pass in the second buffer. You have 5 elements. The type is integer, and then the operation you want to do is the sum. So then rank 0, it's going to print its results, and rank 1 is going to print its results. So let's take a look at this. Local and MPI run. There we go. You see that this is rank 0, and this is the result of rank 1. It's going to be 2. Okay. Coming back here. The reason for this is, of course, obvious because we have initialized it with rank, right? If you take a look at here, we initialize both of them with rank. So on rank 0, it's going to be 0 plus 0. That's an MPI sum, right? 0 plus 0 is going to be 0. And on rank 1, it's going to be 1 plus 1, which is going to be 2. That is the reason. So there we go. We talked about that. Now we're going to talk about reduce and scatter. MPI includes variants of the reduce operations where the result is scattered to all MPI processes in a group on return. One variant scatters equal-sized blocks to all MPI processes. Another variant scatters blocks that they have different size. The size might vary, and you can you might have guessed that in blocking collective communications, usually when you say something may vary, then you need to pass in an array to basically give the size of each block. Okay, MPI reduces scatter block. This is the first version that basically gives the results in equal size blocks. It takes send buffer, receive count, data type, operation, and communicator. Let's take a look at it. Where's the example? I do have an example for this one. Yes, MPI reduces scatter block inter. So I'm not gonna read all these stuff, but you know that this is gonna be like two operations sort of combined. We have a reduction and we have a scatter. So let's take a look at it. Vim MPI, what was the name of it? I forgot it again. Reduce scatter block. Let's see. So we have an intra-communicator and intercommunicator, these two scenarios. So here we have, for example, oh, this is important, that this is the, so every block, so we said that they're going to send equal sized blocks. So every block is going to be 3 of size of 3. So the send buffer should be a multiple of 3 in this case, because we want to receive 3 blocks. If you wanted to receive, for example, 4 blocks, then the send buffer should be a multiple of 4. So 4 times the size. And then the receive count, that's the count of the arguments that you want to receive, is going to be 3. And then you populate the send buffer with sort of uniquely with a combination of rank and also the, what's it called, the loop iteration counter. And what you try to do is you do this reduce scatter. So you're going to do a reduction, and the reduction operation is going to be MPI sum. So you're going to calculate the sum, but then you're going to scatter the results. And once you scatter the results, then it means that every process, it's going to get its own share. In this case, everybody is calling this from elements 0 to 3, and everybody is going to get its own share of sort of scattered results. So you're going to see this example is actually a beautiful one. MPI CC MPI reduce, up, scatter block, let's see, MPI run with 4 processes. You can see that we used a sum operation, right? So process number 0 gets 3 elements. That's why we have 3 statements by process number 0. The first one is going to be 6. That's the result of summation of 0, 1, 2, and 3. But if you remember, once we initialized our send buffers, we had a rank plus I, the iteration counter. So the next count is going to be 1. So every process is going to put 1 on top of that. So 6 plus 4 is going to be 10. Again, 10 plus 4 is going to be 14. Then we go, so these are the portion, the scattered portion to process 0 or the root process is 6 and 10 and 14. And then the portion for process number 1 is going to be 18, which is like, again, you see that every process puts one on top of that. That ends up in 18, 4 on top of that, 22, 4 on top of that, 26. That's how we end up with different values. And you can also see that there is no, in printing, there is no order of processor 0 to be printing first, then process 1, then process 2, then process 3. Okay, so that was reduce scatter. Again, this that was reduce scatter block, which basically performs the reduction and then scatters the results. Scatters the results based on the ranks of the processes involved, and it scatters the results in equal sized blocks. So every block had the size of 3 in this example. But we're going to have another version of it, which is called as MPI reduce scatter, which gives you flexibility to have an array of receive counts. So this is going to be of length group size, that's an array. And this receive counts is going to be an array. So in this case, I do have another example of this one. So let's take a look at MPI reduce scatter block inter. So the first example we saw was in the scenario of intra-communicator when all processes involved are going to participate in the reduction. But in this case, we're going to have that scenario of intercommunicator, group A and group B. Then all the things up there are basically that making the process of group A and group B. And then we're going to have the same story here. We're going to have a receive buffer of 3 and a receive count of 3. But then the send buffer is going to be a pointer this time because group A needs to allocate proper spacing based on the size of the group B, that is world size minus local size, and multiplied by 3, of course, because we want to have 3 elements, right? And times size of integer because these data are basically integer data. So that is what is happening. So this is group A, which populates the send buffer with the world rank plus I. Again, a combination of rank and the loop iteration. And group B is going to do the same, but this time group B is going to use the size of group A. So group A uses the size of group B, and group B uses the size of group A. That's why we have 3 times local size. So these intricacies are super important, because when you take a look at the standard, there are no examples in the case of, you have seen that here, for example, we didn't have any notion or any example of intercommunicator. So this example is super important and very beautiful one. So the semantics are super important. You need to understand that what is going on. So we have a reduce scatter block. Everybody's going to get its own share with equal size blocks. But group A, does it matter when we are using even numbers for the number of processes? No, it doesn't, because world size minus local size is going to be the same as local size. But when you are using odd number of processes, then these two values are going to be different, and that is exactly when it matters. Then you perform your MPI reduces scatter block. The only difference is that you're not passing an intra-communicator like MPI comworld, but you're passing the intercommunicator. And then you see that color 0 is the group A processes. They're going to print their own results. And group B, they're going to print their own results. Again, this thing is, I think we have used MPI sum. So it's going to be summation of, let's say, interchangeably groups of A and B processes. So let's go MPI CC, MPI reduce scatter block intercommunicator scenario, and we're going to run it with 4 processes. You see that, for example, proc 0, initially it returns 5. Why? Because group B has processes 2 and 3. So that is why we have 2 and 3 summation is going to be 5. Again, we are using a combination of rank and the loop iteration. So in the next element is going to have basically 1 plus 1. So that's going to be 2. 5 plus 2 is going to be 7. Then it's going to be 9. For process 1 is going to be 11. It's going to be 13. The next. And then process B starts with 1. Why 1? Because in group A, we have process 0 and 1. And summation of 0 and 1 is going to be 1. And in the next, because we are using the combination of loop iteration, the loop iteration is going to be 1. Then it's going to be 1 plus 1. Whoops. So this thing is almost over. I'm going to finish this example, and then we're going to continue in the next part. So that is why we get a 3 here. So plus 2 here, plus 2 here, plus 2, plus 2. That is how it basically works. In fact, if you go back here and, for example, go back here in the send buffer, you basically remove this, then you're going to end up with the same results. You see that all processes in group A are going to get value of 5, and all processes in group B are going to get the value of 1, because that's the summation of 0 and 1, and this part is summation of 2 and 3. Okay, so let's bring back what we have deleted. Okay, we're going to continue in the next part.